concept of temperature. And of course, you already have a really good intuition for temperature, and you probably have been using the Fahrenheit temperature scale your whole life. So you have an idea when you walk outside, let's say this week on Friday, and you knew that it was much closer to 65 degrees than it was to 35 degrees Fahrenheit. But what is temperature? Temperature is actually a measure of the total internal energy of a system. That sounds very strange, but it's true. And in fact, in order to make this definition work very well, we have to use a different temperature scale. So the units that we need to use are Kelvin. These are the units at which the temperature units are proportional to energy. And we'll be using this concept later, and you'll see it later. But in order for thermodynamics to work, you must use the temperature scale of Kelvin in order to do the manipulations that we're going to talk about in this class. That doesn't mean that you can't be given a temperature in Fahrenheit or in Celsius and then have to convert them to Kelvin, but you will have to convert to Kelvin before you do any of the problems for this unit. So what is a Kelvin? Well, 1 Kelvin is 273 degrees Celsius. And of course, you can figure out how to convert between Fahrenheit and Celsius by literally just putting it into Google, and it will actually do the calculation for you. So we're not going to go through that. It's not actually even a useful exercise. Most interestingly is that 1 degree change in Kelvin is equal to 1 degree change in Celsius. So even though the scales are shifted, the change in temperatures are similar. So that means that the Celsius scale, which is the one in which we put freezing at 0, freezing of water at 0 Celsius, and boiling of water at 100 Celsius, that temperature scale is actually closer in some sense to being proportional to the energy, in the sense that the change in the temperature, let's say between 0 Celsius and 100 Celsius, is the same energy change that you would get between in this case, 273 Celsius and 373 Celsius. The energy change would be similar. Let's talk a little bit more about temperature. So we just said that temperature was a measure of the total internal energy, and it's true. And in fact, temperature is something we call a thermal property of the system. So thermal properties are properties that a system can have, and that help to describe the state of that system. So we can say that we have some air inside of a balloon. It has a certain temperature, and that's a property of the air inside the balloon. There are other thermal properties that we will be talking about, which you've probably seen in thermodynamics before. Volume is one, pressure, number of particles. And what's interesting is all these things change when heat is transferred. They describe the state of the system. Thermal properties are related to one another through an equation of state. This is an equation relating the thermal properties by definition. In this case, the equation of state is the ideal gas law. You may have seen this before, but you can see very clearly now that we've defined it this way that it's relating the pressure, the volume, the number of particles, and the temperature. So again, this P is pressure, V is volume, N is the number of particles, and T is the temperature. This constant Kb, which is given multiplied by temperature and the number of particles, is Boltzmann's constant. It's equal to 1.38 times 10 to the minus 23. We're going to talk about the units of all of these things later, but obviously the units of all of these things are important, but I'm not giving them to you now. We can also write the ideal gas law in terms of the number of moles, because we typically don't just talk about 1 or 2 or 3 particles. We're talking about some very large number of particles on the order of Avogadro's number, which is 10 to the 23. So it doesn't make sense to talk about the number of particles all the time and use that Kb constant, which has this very small exponent on it. Instead, we can convert the number of molecules to the number of moles using Avogadro's number. And in the same calculation, we can see that the ideal gas constant, which we now call R, is now 8.31. And again, the units are going to change of this ideal gas constant when we use R compared to when we use kBt, and we'll talk about that shortly. So we've been talking about ideal gas law, but what is an ideal gas and why are we using it? So an ideal gas is, in a sense, you can think of it like a model system. So in biology, you use model systems all the time, right? You'll use a mouse model or a fly model in order to understand how a disease works or how muscles work. This is the same kind of idea. In physics, though, our models are just much, much simpler, probably because we're just more simplistic people. We don't like looking at very complex systems, so we're going to look at things that are really not complex. So we're going to assume that we have an ideal gas which is made of perfect point particles. You can think of them like little tiny miniature billiard balls. And these billiard balls are actually non-interacting, which means they can pass through each other. So as they move, you can see they can just move right past each other and they don't interact with one another. We also can assume that we can count all the particles and that we have some idea of how many there are. And again, we can either use n, the number of particles, or little n, the number of moles of those particles. These particles are moving. They have kinetic energy and momentum. So we're going to come back to those concepts again today. And these particles can interact with the walls of their container. So if they bounce on the edge, that interaction will have not only conservation of momentum, but it will also have conservation of kinetic energy. So we're assuming that they're not going to slow down after bouncing off of the walls of the container. And that means that they're going to have elastic collisions with the container. So again, we're bringing in all of these concepts that we just learned about in both energy and momentum in order to understand these particles. But you can see that this is a very idealized view. In actuality, real gas molecules have internal degrees of freedom. They do bounce off of one another. And so we're making a lot of assumptions here about this gas, which are just simply not true. But we're going to use them anyways. So let's now go back to our equation of state and look at all of our thermal properties that we have. This volume that we've talked about, it should be measured in meters cubed. Again, a meter, remember, is the SI unit for distance. And so if a volume is obviously a distance times a distance times a distance, so we should use meters cubed. You'll also use liters, and you can convert liters into meters cubed, and you should do that. And capital N is the number of particles. This actually has no units because the number of particles is a unitless parameter in the SI units. But little n, the number of moles, actually does have a unit, which is moles. And we can get the number of moles by dividing the number of particles, capital N, by Avogadro's number. So just to remind you, Avogadro's number is equal to 6.02 times 10 to the 23, and it also has units of particles per mole. So because particles is actually not a unit, its units are actually per mole. But I would suggest that you always write the word particles, and just remember that particles is something that you can cancel when doing this manipulation. The pressure is a very, very interesting property because it's actually equal to the force per unit area, and it has units of Newton per meter squared. Newton per meter squared is also called pascals. It's denoted as capital P little a. When you talk about the force, about pressure in this class, we need to use pascals. You may be given pressure in other units. There's a variety of other units such as millimeters of mercury or something like that, or you can talk about atmospheres. Atmospheres are useful because obviously at sea level on Earth, 1 atmosphere is the pressure due to the air around you. But this should always be converted into pascals when doing your calculations in order to make sure that you're getting the right numbers. These constants that we talked about earlier also have units. KB, which I gave you as 1.38 times 10 to the minus 3, actually has units of joules per Kelvin. Now that we're seeing the joules, you can see that there's going to be energy involved in it. And this is very important to think about. Joules per Kelvin, that means that if you multiply KB times the temperature in Kelvin, which we've already talked about the units for, you'll get back joules. We can convert the equation of state from the number of particles to the number of moles by multiplying by Avogadro's number, which is particles per mole, and that gives us, so if you multiply this 1.38 times 10 to the minus 3, and you multiply by Avogadro's number, 6.02 times 10 to the 23 particles per mole, you get this R value of 8.31. By definition, of the equation of state and the definition of Kb, you can now see that the units for this R are joule per Kelvin mole. So this Kelvin and the moles are both on the bottom in the denominator of this equation. So that now when you multiply it by little n and t, you just get joules.